Homework 2, section 2, So that's chapter 2, section 2. You'll notice we're skipping chapter 1 entirely. And we're skipping section 1 from chapter 2. Chapter 1 is basically stuff that it's basically just functions, which I've been harping on for 2 years now. And the whole reason I've been harping on it for 2 years is so that we could jump right into this. So I think you guys should be good. If you want to browse and look and just make sure, that would be a good idea. Section 1 from this chapter is basically introduces the idea that I did last time, the idea of a tangent line and speed, right? And so rather than go through and do a bunch of calculations like the homework that's in that section, just gives you a bunch of points like you would have. And then you'd be calculating the slope between this one and this one, the slope between this one and this one, the slope between this one and this one, or the slope between this one and this one, and compare that as you do the slope between this one and this one. Compare that to, and it's just busy work. I don't think there's much to it really. I don't think you're going to get much benefit from it, as long as you understand the main idea, which is this right here, that you have some function, and you want to know what is the slope of that function here at this point, x. We want to know what's the slope of that guy. So what do? We go a little bit beyond x. How far? Call it h. So you're at this new place, x plus h. So your distance from there to there is h. You plug that in, and now you have a rise that you could compute, f of x plus h minus f of x, and you have a run of h, right? Yeah. That makes sense, right? And so then the slope from there to there, call it m, can be given by this, f of x plus h minus f of x all over h. Everybody get that? Yeah. And then the idea was, the smaller that we make h, as h gets smaller and smaller and smaller, then the better and better that approximation becomes, right? This, by the way, is called a difference quotient. Or the difference quotient. There's a difference, and there's a quotient. I mean, that's pretty good, right? Okay? And so, indeed, what we're going for here, as I've kind of been hinting at for a while now, the idea of making that h really, really, really small. What I mean that explicitly what we're going to do is we're going to take a limit as h drops down to 0 of this thing, whatever this is, x plus h minus f of x all over h. And what that would give us, now Noah brought up a very interesting point. He said it can't be 0. You can't let h be 0. You'll get junk, and that's true. And today we are going to define a limit, and you'll see that the way we define it explicitly takes care of that problem. And so, Noah, your intuition was right. It is right. You just can't just have h be 0, right? Our definition of limit will take care of that, okay? And what this would give you, if you take this limit, if you imagine that you can take h all the way down to 0, you'll get something. And it would be the slope of f of x at whatever number x. And you'll notice I just chose some random number x. I just said that one right there. I could have chosen that one. In other words, x is a variable, right? And so what you get out of this is a function. Last time we called it g, right? It was the speed function. Given that f was your record of where you had been, or where you were, right? G was how fast you were going at that point. Is all of this making sense? Right? That's the thing. If you were to do this at any given point, you just call it x instead of calling it 3 and then plugging in a 3 and doing all of that, and you find out. Or what were we doing last time? It was at time equals 1, right? And we did some calculations and found that at time equals 1, you got that the slope was 30, right? The slope of that line that touched at one point was 30. Well, now instead of saying at 1, what if it's just any one of them? It would depend. Like when we calculated it for 1, we ended up with a 1 plus h squared and other stuff minus 1 plus or minus 1 squared, blah, 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 blah. But you could, instead of saying 1, you could have put an x for each one of those. And it calculated some stuff, and an h probably, hopefully, would have dropped out. And then you'd get some kind of function in terms of x. Right? And so that is half of calculus right there. That idea right here, that we could take some kind of limit, whatever that is, we're going to define it in a minute. If you could take a limit of this process right here, what you get is a function which will tell you the slope of this guy at any given point. But it's nice to think about that as like your speed, right? This is what we called our speed function last time. Right? It has, and we'll get into, there's precise names and everything for that, and blah, 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 blah. Okay, so that is the goal. The first half of calculus, that's the goal, is to develop this idea right here. This speed function has a special name. It's called the derivative. First half of calculus is called derivative calculus. Then going in the opposite direction, we call that integral calculus. So when you have the record of the speed, how do you get back to your original function? This is, you have your original function, how do you get a record of the speed? Okay, and so this is what's motivating the discussion for today. We want this. This is our goal. We want to be able to develop this. Give me any function in the world, and I want to be able to get a new function out of there that tells me the speed at any given time. And by the speed, I mean the slope of this tangent line right there. Everybody with me so far? So, okay, so I've motivated, this is our motivation for doing this, okay? But in order to do this, we need to define what a limit is. All right. But that definition, the rigorous definition, is a doozy. It is rough. I could put it up on the board right now. And in fact, we're going to go into it. It's like in section 2.4 or 2.5. We will go into it. But it's more valuable to start with a hand-wavy definition. I mean, like a not-so-rigorous definition, which is what we're going to do today. Why? Well, what's the definition of addition? Do you guys know? Have you ever seen a definition of addition? Like 2 plus 3, what are you really doing there? Turns out, like, to develop a rigorous definition, you need like 200 pages of stuff. You define what's called a successor function, and et cetera, and it's ridiculous. Like, and if I were to try to explain that to Peter, like, okay, Peter, addition is this process by which we have what's called a successor function, which given any integer gives you the next integer. So to take 2 plus 3. First, we have to, no, you can't do that. You'll never learn addition, right? You say, well, if you have this many and you have this many, you put them together and count them. That's what addition is, right? Same thing here. We're going to start with I don't want to say kids version, but like, a less rigorous version of limit. That way you could actually work with it, see what you're doing, do some calculations, and then you start to get a feel for it. Then we'll jump into the rigorous definition, which you'll never see again until you take analysis. Actually, later on in this class, we will use the definition for at least one thing, because no calculus text I've ever seen proves this thing that's so important. And of course, I'm going to do that, right? That's what I do. And so we're going to do that. We're going to use the rigorous definition, but again, it would be like, just same way, like, you guys are doing just fine, and you don't know what addition is. You're good with limits. Like, and this definition that I'm about to put up here is sufficient, and it's the way I think about it, unless I'm doing something in analysis, in which case you gotta pull out the rigorous one, blah, 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 blah. Everybody with me? Yes. Okay, so, definition. This is coming straight out of the book. A lot of what I'm doing today is coming straight out of the book. we write lim x equals L. And say, quote, the limit of f of x, the limit of f of x as x approaches a equals L. That's how you'd read that. The limit, and you could mix that around. Like I'll often say the limit as x goes to a of f of x is L. But this is the technical way of saying this, okay? If, so we will say that this is true, this is what this is defined to be, if the following is true. If we can make values of f of x arbitrarily close, and by arbitrarily close, we mean, or we'll say arbitrarily close to L, and by that we mean as close to L as we like. Meaning like, if L happens to be 5, can we make f of x 4.999999999? That's what we mean arbitrarily close. As close as you could possibly want, within any tolerance, is another way of saying that. You could do that by, well, how? How? By doing what? Well, by taking x sufficiently close to a. On either side of A. Okay? This is, I'm going to draw something and this will make make a lot more sense. Okay? You think about x being on the x-axis and you have some A there. By arbitrarily close or sufficiently close, we mean getting close, but on both sides of A. Okay? I want to get this definition up and then we'll actually talk about this. It'll make a lot of sense. But, and this is key here, but not equal to A. Okay? So, you have some function. There's some number A right here. And when you plug it in, I guess you get out f of a or whatever it is. But what we're saying here is that, so if this is f of x right here, we say the limit of f of x as x approaches a means that you give me any distance away from L right here. Maybe L itself or whatever, right? Like, and I could find an X. I could tell you how close to get to A that will get you that close. Okay? That's what we're saying here. This very much is like the rigorous definition. It's a little bit, it leaves a little bit out, like this there's some formalism there that I'm leaving out deliberately. But let's, now, just before we move on, because I'm going to erase all this in just a second. But here's some notation you've seen before. Another way of saying the same thing is that f of x goes to L as x goes to A. Does that look familiar?
Yes.
We did that in trig, right? And we had stuff like sine x goes to 1 as x goes to pi over 2, right? Yeah. Now, if you remember, we also did interesting stuff like this. So if we think about sine would look this. And so there's a secant or cosecant. Cosecant. We also did stuff like this. So here's pi, right? Pi is where that is, because this guy's pi over 2. This guy's 3 pi over 2, right there. And we also said stuff like this. So cosecant x goes to positive infinity as x goes to pi over 2, but we said from the left, right? Remember that?
Yeah, goes to
right?
pi.
And, oh, yeah, thank you. As x goes to pi from the left, meaning as you go from this way, you're getting bigger and bigger and bigger and without bound.
So from the negatives.
From the left, we say from the left. And there will be another definition in a minute where we're going to say either from the left or from the right. But it goes to negative infinity as you go to pi from the right.
Yeah.
And these mean the exact same thing here, right? So I could write, well, we'll get into that. So, okay, I'm going to get rid of all of this and we're going to do some actual examples that will kind of tie this up. Any questions before we go? No. Nope. Okay, great. All right, here we go. First example. And, okay, I'm not always going to write f, but if I do something like this, limit as x goes to 2 of what? X squared minus x plus 2. If I refer to f, I'm talking about this function right here. We're going to pretend that f is this guy right here. So the limit of this, now right here you could say, well, I just plug in a 2, right? Like you could just plug in a 2 into this function. And you could do that. And you would be, the thing that you get out when you do that would be correct. There's a problem. The definition of the limit says that you cannot just plug in a 2, right? This will be more clear in the next couple of examples why that matters. But right now, we're going to say, here's my f, right? There's that function right there, x squared minus x plus 2. And I want to know what happens as this guy goes to 2. Now, again, in the definition, it said that it has to be the same from both sides. Right? So what you're going to do in your homework for these questions like this is you're going to make a table. I suggest that you use a calculator. One of the few times I'm going to suggest that you use a calculator. Right? How many times have you, in the last 2 years, how many times have you guys used a calculator? Like yeah, right? Like twice, okay? Well, this is one of those times, okay? So we're going to make a table here. And again, after we do like this section, you'll never do this again. You'll never do it this way again. But like I said, it's good, like with math, when you first learned addition, you probably actually used your fingers. But you don't anymore, right?
Yeah, usually.
I do sometimes. But I mean, usually you don't, right? So this is like using your fingers, because it's a good idea to go ahead and like see what's happening here, right? So the idea is this: we want to go from 2 different sides towards 2. So I'm going to start here at 1, okay? And I'm just going to plug in 1.0 into my calculator, right? And go 1.0 squared minus 1.0, well, I guess just 1, I'm not going to put the 0.0, plus 2, and what pops out is a 2.0. So then I do the same thing, but now I'm going to go 1.9, because I'm getting closer, right? I started here, and now I'm going to 1.9, right? I plug in my 1, I get out a 2. I plug in my 1.9, and I get out a 3.710. Okay, so there's my 3.710 right there. Then I'm going to plug in a 1.99. Plug that in, I get 3.9701. Okay, so I plugged in something even closer to 2, 1.99, and I get something that's getting, what does it look like it's going to?
4.
It looks like it's going to 4, and yeah, indeed, it if you were to just plug in a 2, you'd have 4 minus 2 plus 2. It would give you 4. Okay, so that looks good. That's what we expect, right? But we're talking about limits now. So we're not just talking about plugging a number into a function and seeing what the output is. Though, in the very near future, that's probably the first thing you're going to do. If you're given a function and you want to just check the limit, you're just going to plug in the number and see, did anything blow up? Right? Because you'd have a problem if this was your function right here. Can't do that, really. Can't just plug in a 2. Here you can just plug in a 2. So in the real world, you're just going to see, can I plug it in? Okay, I'm good. I'll just do that. But again, this is like we're using our fingers here. And there's rhyme, there's reason to this rhyme here. Okay? Or method to this madness. Now, okay, so it really looks like it's going to 4. It really does. Okay, now we're going to go from the other side, and I'm going to start here at 3. I plug in a 3 and I get out, is it an 8? Yep, I get out at 8. Okay, now I'm going to start moving down by the same amount, and I'm going to go down. So I started at 3, got out an 8. Now I'm going to jump down to 2.1. Plug in my 2.1, and I get 4.31. Okay. So again, right, these, as I was going in this direction, they got closer and closer to this value 4. Now I'm coming from the opposite direction, right? I plug in my 2.1, I get out a 4.3, right? Now I'm going to go 2.01. I plug that in, my calculator tells me it's 4.0301. So I plug in something closer, and it brings me closer. I plug in 2.001, and I get 4.003001. Plug that in, I'm getting closer. What does it look like it's going to?
4.
Do they agree?
Yes.
They're going to the same place? Okay, then we could say, yes, the limit is 4. By definition, we can't just plug in the 2. So you see how this takes care of your problem with the 0? Like, you can't just plug in a 0. You're right, but you'll see in the next example, you'll see, well, maybe in a couple of examples, you'll see how you can't just plug that in. It'll give you division by 0. But if you do this, you'll find, oh, it actually doesn't do that. It actually does give you something that's not junk. Interesting. So, and we'll see why in just a second, okay? So, okay, you're going to be doing that in your homework a lot, and sorry, but it's good. It's actually good to do. Like, but let's get a little bit more abstract, because that was, like, that was a function into which we could have just plugged a 2 and we'd be fine. There's no problems with plugging in a 2 into that function. Now, here's an example of when that... What is that?
It's my friend's alarm or something.
Okay. Alright. Okay, so here's an example of a function where you can't just plug in the number. A hole in the graph. It's not defined there.
Oh.
And let's say there is a 3. And this function is f of x. Okay? You can't just plug in a 3 because it's not defined there.
Could be.
But what you could do is this. If you happen to know where that is, let's say it's a 2 right there. Well, you could just see from the graph, and you'll be doing this too, as x gets closer to 3 from this side, the values here get closer to the number 2. As you approach 3 from this side, the values here, the output values, also get closer to 2, right? Go from this side, and it's getting closer and closer this way, which means that they're, in both cases, moving closer and closer to the value 2. So that is what it means to have your limit as x goes to 3 of f of x equals 2. Now check this out. This is what's This is one of the hard things. This is a perfectly good function. It just happens to not be defined at 3. We could take a limit to see what happens as it goes. That's cool. But what if it is defined at 3? What if it's a jump? You'll see this in your homework. That's a perfectly good function. It's defined. It just happens to be a jump. It's not continuous, but there's a jump. It's called a jump discontinuity. Okay? And, well, what do you do with that? Well, it happens to be the case that if I plug in a 3, I get out a 1. But it's still the case that the limit is 2 there. Interesting. Because, again, limits don't care about this. They only care about, hey, which way am I going? Which direction am I heading? Am I heading in this direction? Well, then I'm heading towards 2. It doesn't know that this is happening because it's at that place. And by definition, we don't care about what happens at that place. So as you come from this direction, as far as the limit's concerned, hey, I'm going to 2. I'm heading closer and closer and closer to 2. As far as it's going from this way, I'm heading to 2. Closer and closer and closer to 2. Well, it agrees on both sides, so the limit's 2. Everybody got that?
Yes.
That's going to be, you're going to have that in your homework. Like a bunch of that. Like, they'll give you a graph and they'll say, what's the limit? Well, don't be confused just because there's a jump. All that matters is the behavior as you approach from either side. Okay? Here's an example. And this will help with, I think, seeing why what we did yesterday or 2 days ago with the H, why I was like, no, it'll cancel, trust me. Don't worry about it. Like, this maybe will convince you more. Because watch what we're going to do. Okay. Oops, no. Sorry. Finding a function. We're finding the limit of that function. Finding the limit as x goes to 1 of what? X minus 1. This is my function. I'm going to refer to it as f. F of x. Find that limit. So in other words, this equals what? Find the number it equals. And we're going to do this 2 different ways. In your homework, you're going to do it the first way. The first way is going to be plugging in the values, right? Plug in vals, make table. But then for the rest of your life, the way you're going to do this is algebra. Algebra and reasoning. Which is coming later, not in this homework, but this will tie everything
So
together.
all we're doing for this homework is plugging in, is making that table. Okay.
At least for this part of it. Well, there are other ones where I just drew that graph up on there, and I was like, "What's the limit?" Well, you're not plugging in values for the graph, right?
Okay.
Like when you have something like this,
Okay.
you're not plugging in anything. You're just looking and saying, "Well, it's going that way, going that way. If that's a 5, it's going to the 5." So that's all there is to that. But when you have something like this, and I think it does tell you to do it that way. Making it, yeah, I think they pretty much all tell you to do that. If not, that's what you're gonna do. So, okay, so let's make a graph or a table here. Now, in the real world, the very first thing I would do is just graph this guy. I'd plug it into some graphing software and say, oh, that's what. Okay, well, that's the limit. But you can't rely on that because sometimes the graph will lie to you, and we're going to develop this. So, okay, we're going to 1, right? So I'm imagining, all right, we have some function. Don't know what it looks like, but I'm going to 1. So I'm going to come from this side first, and I'm going to start somewhat close. I'm going to start here at 0.9. Okay. So 0.9, coming from the left-hand side. I plug in a 0.9, do my calculations, I get 0.52, 6316. I plug in a 0.99, and I get a 0.502513. I plug in a 0.999, and I get a 0.50025. And then I plug in 4 9s, 0.9999, and I get 0.53025. What does it look like it's going to? 0.5. It looks like it's going to 0.5. That's my guess. And so, like, if I would have been graphing this, we would have seen, okay, it's coming down from 0.52, okay, and so it's heading, it looks like it's heading to 0.5, and so it looks like it's doing this kind of thing right there. And indeed, if I were to graph this, can I just plug in a 1 here? No. So there would be a hole in this graph. There really would be a hole in this graph. Now, graphing software won't tell you that. It'll just graph it. And because it'll never actually plug into 1. But the pixels that it does will be so close to 1 that you wouldn't be able to tell anyway, right? So, the thing is, that's one of the reasons you can't trust a graph. But if you look at the graph, like, you could probably figure that out. But you have to actually look at this and say, I can't just plug in a 1. Like, this function, like, if I tried to plug in a 1 into this function, I'd be dividing by 0, and I can't do that. So this graph actually does have a hole. And now, though, we have to check the other side, because there might be something funky going on, especially when you have, like, minuses and stuff, because if you're on the other side of something, that might make the denominator negative or the numerator negative or something like that, and so it might be coming from down here. We don't know. It might be actually from the other side going to negative 0.5. This is one of the things you just have to check. So we're going to go on the opposite side. We're going to come from here and descend towards 1. And I'm going to start with 1.1. Plug in my 1.1, and I get 0.47619. I plug in my 1.01. Right? And you notice I'm going by the same amount each time. Over here I'm off by 0.1, here I'm off by 0.1. Here I'm off by 0.01, here I'm and so on forth, right? This gives me 0.497. 497,512. The next one, 0.001, gives me 0.499750. Other one gives me, or I'm sorry, now I plug in go for broke, plug that guy in, and I get 0.49975. What does it look like it's going to? 0.5, right. And so yes, it does actually look like this. This is coming up here, up here, up here. And so we would conclude, just by looking at the data, I'm going to conclude that this limit equals what? 0.5. Okay, that's what you're doing in your homework. And in a second, we're going to see why that's not a very good method. But that's what you're going to do to get yourself used to this. So when the book tells you to do it this way, you do it this way. But in the real world, or pretty much for the rest of this class, we're not going to do it that way. We're going to say, well, hold up. This thing right here, can I factor anything?
Bottom is x plus 1, x minus 1.
X plus 1, x minus 1. Does anything cancel?
X minus 1. Yeah.
And so this is the same thing as this, right?
Yeah.
Can I plug in a 1?
Yes.
What happens if I plug in a 1?
You can't plug in a negative 1.
But before you could have
Oh, wait, yes.
one until you canceled.
Now that I've canceled something out, now I can plug in the 1. Couldn't do it back here. Plug in that 1, blows up. But it turns out that this thing is just kind of in disguise. It's just this in disguise, right? Yeah. Like you just multiplied this thing by 1. 1 happened to be written as x minus 1 over x minus 1. And that messes you up if you try to just plug in a 1, because your computer's going to say, I can't do that. Because your computer's not that smart, right? But we are, and we could say, wait, this. You actually don't have a problem, but technically you do, so there's a hole in this graph. Like you can't just plug it in, so okay, there's a hole there. But you can see that if you do some manipulation here, we can just plug in a 1, and we get 1 plus 1 is 1/2. So we could say then that x minus 1 over x squared minus 1 goes to 1/2 as x goes to 1. And you could check that it works from both directions. I mean, it does. There's no weird squareds or absolute values and crazy stuff. We won't need to worry about that anyway. Does that make sense?
Yeah.
Why exactly does that happen with the? Because they're the same function, right? But why does one not work when you plug in the one?
Well, it's just a technicality. It's just a technicality. It's the same thing as saying 1/2 is the same thing as 6/12. It looks different. It's the same thing. It's just technically, if you tried to plug in a 1, you get division by 0. All right. Yeah. So, does that make sense? I mean, it kind of does. It's weird.
Now you can't plug in negative.
But how can they be equal to each other if one is undefinable and the?
Yeah, because they're technically not.
Oh, they're not.
Yeah, okay, I see what you're asking, yes. Technically, these are not the same thing, because you cannot plug in a 1 into here without dividing by 0, and you can here. But they have the same graph. The only difference is this one has a hole here, because of the technicality. This one doesn't have a hole there, because it's, yeah. And so, when you're actually trying to find a limit, you could just say, well, if I could turn this into something that's technically different, but has the same graph with no holes, then I could just pretend that that hole doesn't exist. And that's what we're doing here when we plug in that 1.
Okay.
You see? This is one of the big headaches of the beginning of this class, is there's stuff like this. But as we move on, we're gonna just basically throw all this to the wind, and it won't show up very often at all, because we'll have the tools to take care of this. So like I just said, later on, we're gonna say, wait, can I turn this into that? Yeah, are there any problems with that? No, okay, move on. And what we're doing here is we're acknowledging that, yes, the actual thing you're worried about has a hole, so technically you can't do that. But we don't care about the thing, we care about the limit. We care about, well, where are we heading? Here and here. And if you could find a function that just simply doesn't have the hole, then you could just plug it in and you're good to go. You see?
Yeah.
So that's what all this is about. And eventually you will completely forget about this whole, does the thing have a hole or not? Because it won't matter later on. Except in some circumstances. But for the most part, you're just going to do something like this and say, we good? Yeah, we good. Okay, move on. So there's that. Okay, questions on that?
Yeah. I mean, no.
Yeah, I mean no. Okay, so here's the thing. So I'm going to go ahead and draw this guy a little bit better. This is what he does. He does something like this. And indeed, right, this was 1 over x plus 1. So it should have been like 1 over x, but shifted over a bit. Or shifted that way a bit, right? And that's what that is. That's what we've done. Okay, so, except that the one we care about has a hole there and at -1. Yeah, interesting. But who cares? That's not the point right now. This is where, ugh, I hate this stuff. Let's say I define a new function. And it's a piecewise function. And this function is defined to be x minus 1 over x squared minus 1 whenever x is not equal to 1. And then you're like, well, I don't want a hole in the graph. So I could go ahead and say 0.5 wherever x is equal to 1, and I'd have a nice smooth function, but that's not necessary. I could just do this. Why would I do that? I don't know. But it's one of those things. And so what would this thing look like? The graph of this thing would have a jump right here. And it would be like this. And so technically, so here, let me ask you a question. G of 1 is equal to? 2. But what's the limit as G? There you go. The limit as x goes to 1 of G of x. We don't care about what you could just forget about that entirely. You could say, well, I don't care. I just want to see what the function's doing. Are they going to the same place? Yep. When you go from the left, it's going to 0.5. You go from the right, it's going to 0.5. So 0.5 or 1/2 or whatever. Okay? Everybody with me on that?
Yes.
Okay, like I said, soon we will not be plugging in a bunch of values. This is just, we're counting with our fingers because addition is hard and we want to get a feel for it, basically. Alright, very soon we won't be doing this. But this will be a really good exercise, especially something like this, which you're going to have in your homework. Here's an example. We're going to estimate this limit. The limit as t goes to 0 of the square root of t squared plus 9 minus 3 all over t squared. Try to plug in 0.
You can,
Right? So,
you can
okay.
plug in, like,
Obviously there's a problem. And I could graph this thing and get an idea, but I really want you to use your fingers for this. Because this will certainly help to convince you that what I did yesterday with that h, canceling out the h and saying, it's good. This will help convince you that that's true, because you'll notice you have something very similar. You have t going to 0. There's the t in the denominator. If you just plugged in a 0, it would blow up. And we could do some algebraic manipulation, the same way I did with the h, and then I canceled it. But then that wasn't satisfying yesterday. You were like, well, but you still can't do that. This will help convince you that you can. Because let's actually plug in some values. And so, okay, I'm going to start by going t, and here's f. I'm just going to call it f. You know what it is. It's this entire thing, right? And I'm going to go from the left-hand side.
plug in a
Negative 0.01.
So, yeah, well, the ones that I chose was negative 0.10. So because we're going towards 0, I'm going to start with negative 1, and then go negative 0.1, and negative 0.01. Okay, so I'm going to move in this way first. So negative blah blah gives negative 1 gives me 0.16228. Now I'm going to plug in negative 0.1, and I get 0.16662. I go negative 0.01, and it gives me 0.16667. Looks like it's going to what?
0.162. Like, with the line.
Kind of looks like it's repeating.
Yeah.
It seems. And if you weren't sure about that, you could do another one, and you'd see you get more sixes. So it looks like it's going to that. This is 1/6.
Or once, yeah.
Yeah,
I think
that's
it's-
1/6. It looks like it's going to 1/6. So okay, what happens from the other side? You always have, well, not always, but very often. Well, you notice that it's squared.
Oh, so
The t's always squared, so you could go through and actually compute it, and you'll find that you go 1.0. Well, of course you're going to get the same thing because you've squared it, right? And you go your 0.1, and of course you're going to get the same thing, and your calculator will confirm that, yeah, this works, and then you go 0.01, and you get 0.16667, and so, yeah. But sometimes you do have to check, because it might be like that your thing, just because of something, you're going to different directions. It might be, you know, but anyway, you'll see that in the homework, definitely. So it looks like it's also going to the same place, 1/6. And so it looks like we're going to answer 1/6. And in this case, that turns out to be true. Problem is this. If you continue on with this, this is like one of the pitfalls. If you were to continue on and say go 1,0,0,0,0,1, it probably won't do it there, but you keep going in this direction. Eventually, this thing will give you 0. Why? Watch what happens. Eventually, you plug in a really, really, really small number into your calculator, something like this, and you square it. It gets really, 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 really small.
Yeah.
Right? And eventually your calculator just rounds that off.
Yeah.
And says that's close enough to 0, so this entire thing is 0. So then you've plugged that into your calculator and it reads it as the square root of 9 minus 3 over some really small number, whatever. It does this first and says, well, that's the same thing as 3 minus 3. Then your calculator says, I'm not going to do the rest, that's just a 0. And your calculator spit out a 0. It's a lie!
Yeah.
Calculators lie because of rounding error. So this is one of the pitfalls of doing this, and indeed, this is why we don't do it this way. It's also one of the reasons why you don't actually do addition on your hands, right? Like, if you're adding 703 plus 1,000, you're not going to go, well, so okay, keep counting. No, but this is good to do it first, so that you'll believe that this happens. Even though, like, you can't plug in a 0, you see it is heading towards something. If you go too far, though, there's a problem. That's why we don't want to develop this as a regular old method of doing it. Though it is a method, and sometimes it can really help you out to do this. The same way that plugging it into a graphing software can help you, and so on and so forth. Okay? So, there you go. Here's another problem with this method. And by the way, all of these that I've done are just straight out of the book. I usually come up with my own examples and stuff. That way, if you wanted to look at the book, you could do. But I really didn't. These are such good examples. I just wanted to plug along with this stuff. Oh boy. All right. Okay. Obviously, you can't just plug in a 0. Something crazy is going to happen. So, what do? Well, you start plugging in numbers, and you do the same ones, right? So you go 0.1. These are the x's you're plugging in. And you go 0.01 and 0.001. And what you find is something interesting, because watch what happens. Pi over x over 0.1. That's the same thing. I mean, pi over 0.1 is the same thing as that right there, right? 0.1 is 1/10. Which is 10 pi. And what's sine of anything pi?
1 or 0.
0. So you plug that in and you get a 0.
There we go.
And then guess what happens when you do this?
Oh,
0.01. Well, that's the same thing as 1 over 100,
No,
so that's 100 pi.
pi.
You plug that into your calculator and you get 0. So you conclude, obviously it's 0. But that's not true. That's not true at all. Because if you had used different numbers, if you had used anything that won't give you an integer, you'd see that what's happening is this thing's bouncing around. And so what you finally do is you say, you know what, I'm just going to graph this guy. See what happens. And so you graph it and it looks like this. Does it come down? Yeah, it comes from here. So it does this.
And you were just doing all the ones.
Oh, all of it, yeah.
Because think about it, right? Like, as you get closer to 0, this number just gets bigger. So basically, you have the entire record of sine. But it's just, you know what I'm saying? Like you're at 0.01, well, now you've made it out to 100 with regular sine. So it just keeps doing that. And ditto from over here, it kind of does this thing, and then this, and this, and this, and it goes, and in fact, this is called the topologist's sine curve, because it has some really interesting properties, especially right here. Like, what's it doing there? What's its value there? It's crazy, right? Like, what's happening here at the y-axis? But that's way beyond what we're going to get into. The point here is that this limit does not exist. And in our class, we are going to write D and E for does not exist. Okay? And you wouldn't say equals does not exist. You would just say that this limit does not exist. Okay. Why does it not exist? Well, this is like what we talked about, or what I said in the summer, right? Which is like, what's the limit as x goes to infinity of sine x? Well, it never settles down, does it? It just keeps going back and forth from 1 and 0 forever, or 1 and -1 forever. That's what's happening here. As you go in this direction, it's going from 1 to -1 forever and ever, so it never settles down. It never gets, like, let's think back to our definition here. Our definition was that we can make f of x arbitrarily close to L. We can make it as close to L as we like. There's no one number that this gets arbitrarily close to by going further this way towards 0. It just bounces back and forth. So there is no limit. That's one way that a limit might not exist. Okay? Well, in just a second, we're going to see another way that a limit doesn't exist. Okay?
It's just a straight line.
What now?
If it's just a straight line,
It wouldn't.
What's a straight line?
like if the function were just a straight line, it wouldn't have a limit.
Well, it'd be equal to 0, but it wouldn't.
Depends. If it were a straight line this way, so if f of x were
Y
3,
equals-
Like it'd just be equal to.
that's fine. It would just be, the limit from anything would be 3, because it's always arbitrarily close to 3.
Oh.
Yeah.
You know, if it were this, well, where are you going? You going towards infinity? Well, then there's no limit. Going towards negative infinity? No limit. But if you're going towards, say, 1, then there's a limit, because you're going this way. See what I'm saying?
Yes.
Yeah. But we're counting on our fingers right now. This will become very clear as you start to do this stuff. One more definition for today. Actually, 2 more, but I'm going to put them both into one. Here's another definition. Lim as x goes to a. See that minus right there?
From the left.
From the left, thank you. Of f of x equals L. We write that and say the left-hand limit. The left-hand limit of f of x as x approaches a from the left is equal to L. We say that, we write that, and we say that if we could make f arbitrarily close. And by the way, by f, we were talking about the outputs of f, right? If we can make those outputs of this function arbitrarily close, by taking x, that is taking x values, all right, just like what we were doing. Think about as now hopefully the way I phrased this makes more sense. We had tables, and we kept making those, the input numbers closer and closer to the thing we cared about, right? That's what this means. By taking x close, we could make the output values closer to that. You guys get that?
Yeah.
Right? That makes sense. Now you kind of have a visual for it. Okay. So by taking x sufficiently close to a, and here's the key, less than, that is not equal to a, right? That takes care of that whole hole in the graph thing, right? Like, or plugging in a 0 and dividing by zeros. Like we don't want that. Remember the motivation for all of this is we want a tangent line, but we don't want to divide by 0. So what do? Well, we'll just say that you can't do that. And if you don't do that, well then we don't need to worry about this whole dividing by 0 thing. That's like the motivation for this part here, right? You can't just plug in an a, okay? And ditto, I'm just going to do this, ditto. This is all part of the definition, or you could think about this as the second part of the definition, or a second definition. Ditto. But instead of all the left stuff, we're going to say right-hand limit. And so on, right? Like all that stuff. And then instead of less than a, it would be greater than a. And we've already done this. This is why I'm not really worried about this, right? Because we've done stuff like this. F of x goes to L as x goes to a from the left, or as x goes to a from the right. We did this in trig, so we should be familiar with this. Okay? Okay, so here's an example. So we have this, right? Now this is not negative a, right? And like in the book, I get confused because sometimes it'll have limit and it'll be like -3 minus or -3, and it's just the negatives just kind of mess you up. Just be careful, okay? Be careful with that. But here's an example, and we are actually really good on time. That's excellent because we are pretty much done. Here's an example. So I'm going to draw you a function. And you tell me, I'm going to ask you 2 questions. The output here is a 2, and this is here at 1. And the output there is 3. So, here's a question. Oh, and by the way,
have 2 different.
Oh yeah, functions do that. Straight up there, and there are very, very useful functions that do that. Like functions that are fundamental in some way. There's one in particular. It's in your book too. It's called the heaviside function, which is like this. This is where it's been shifted over to 1, but. I'm not sure if the hole is here or here. I don't remember. But it's something like this. It just jumps up to 1. And like this thing shows up in like quantum mechanics and all kinds of crazy stuff.
What's the equation?
It's called the heaviside function. That's it. It's f is equal to 0 if, so it's a piecewise function. If we're in this range here, or it's actually it's forever, I believe, technically the heaviside function. I'm not sure, I don't remember, right? But if x is less than 0, and it's 1 if x is bigger than or equal to 0. So there's a hole there and a dot there. So this kind of stuff happens, and it shows up in the real world. Yeah. So this is a real thing. Now, if I plug it, here's a question though, and I wanted to make this a 1. We'll call it a 1. Here's my first question. F of 1 is equal to what? 3. Because you plug it in, it's defined right there. That's what the filled in circle means, right? But now, here's the question. The limit as x goes to 1 from the left of f of x is equal to what?
2.
What's the limit of f of x as x goes to 1 from the right?
3.
It's what?
3. Oh, yeah.
3, right? Yeah. So you're just imagining, right? You're plugging in values, so what's happening? Well, as we approach from the right, and again, you're basically everything that's happening at 1, you don't even need to consider. It doesn't matter which one it goes to. You're just asking yourself, well, what am I getting closer to? Well, in this case, I'm getting closer to 3, so the answer is 3. As I'm going from this way, I'm getting closer and closer to 2. Again, don't care about what's actually going on there. I'm just saying, well, as far as I know, as I get closer, I'm getting closer to 2. So there you go. Now, and so, what is the limit as x goes to 1 of f of x? Turns out this does not exist. There's no way to reconcile these two things. You're going from this direction, you're going one way. You go into this direction, you're going somewhere else, well, then they don't reconcile. And now this brings us to our final thing. This right here. This is for any A and any F and any L. The limit as x goes to A of f of x is equal to L, if and only if both the left and the right hand limits go to that exact same number. And I've been saying that the whole time. This should come as no surprise to you, right? Every time I say, it's going from there, we go from the other direction, we're going to the same place, therefore that limit exists. But it has to be the same from both ways. And if I brought that up at the beginning, we would have had to start by talking about piecewise functions. I didn't want to do that, right? Does this make sense?
Yes.
Okay, so you're going to have a bunch of questions about this kind, like this is going to come into play. And it'll say like, if the limit doesn't exist, explain why. Very often it'll be, well, because going from the left-hand side you get 8, going from the right-hand side you get 5, and so this limit doesn't exist. All right. Everybody good to go?
Yeah.
All right. Thank you very much.
Thank you.